Okay, so welcome to the next class of functional analysis. So today we'll be looking a bit further into the space, the vector space, B xy, so where x and y are normed linear spaces. Okay, so morally what we had said is that t is in B of xy if t is going from x and y, x to y, which is a linear transformation, such that the norm of t, which is equal to the supremum of x in B1, is of the norm of t of x in y is less than infinity. Okay, so this is the space B of xy. What we saw last class is that this has a few generalizations. So x in B1 just means all of the x in x, such that the norm of little x in the norm of x is less than 1. Okay, so something that we had announced last class and we're going to do right now is the following theorem. If x and y are Banach spaces, then B x y is also a Banach space. Okay, so how do we prove this? Okay, so the fact that B of xy is a linear space, we proved last class. B xy is a linear, it's a vector space. We proved last class. So okay, by this I mean that if you have t and s in B of xy, then the sum of it is also in t of xy. Also, it has a norm, so it's a norm vector space. So what we need to know, the only thing that we need to show is we need to show completeness. We need to show completeness. So we have Tn, which is a sequence with n in n, which is a subset of B of xi, such that Tn is Cauchy. Okay? So then the point is, can we find a limit for Tn within B of xy? Okay, so the point is now we're going to use the Banach property of x and y to actually get something. Actually, we probably only need the Banach property for y, but let's look at that. So first of all, how do we find a candidate for the limit? How do we find a candidate for the limit? So what do we know? So we know that Tn is Cauchy. Okay, so the question is Tn of x Cauchy for every x in x? Okay, so what we need is that the limit of Tn of x admits a limit. Okay, so if we know that Tn converges to a limit t, then we also need the pointwise convergence of Tn of x to t of x. Okay, so we should know that Tn of x minus Tm of x in norm y is less or equal than Tn, the norm of Tn minus Tm in b of xy times the norm of x. Okay, so then Tn is Cauchy in b of xy means that for every epsilon there exists an n such that the norm of Tn minus Tm is less than epsilon for every n comma n bigger than capital N. So in particular, this implies that Tn of x is Cauchy for every x. Okay, this follows from this inequality here, because now we are looking at the sequence Tn of x minus Tm of x, so An minus Am. This is less or equal than the norm of Tn minus Tm, which can be made arbitrarily small. Okay, so this guy actually, this Tn of x is also a Cauchy sequence. Then, by completeness, of y, we have that for every x in x, there exists T of x, which is a member of y, which is equal, and this is by definition now, the limit when n goes to infinity of Tn of x. Okay, so what we have done now is we found pointwise candidate for the limit of Tn. Okay, so we have found a pointwise candidate for the limit of Tn. So what is the problem? So we do not know if T is even linear or bounded. Okay, so the point is we have created this operator. So this operator is by means of taking the limit when n goes to infinity of Tn of a certain x. Okay, and this induces an operator T of x, where T is going from x to y and is defined by the previous formula here. But nobody has assured us yet that T is linear or bounded. Okay, so the point that we're going to follow now is that actually it's fairly easy to see that it's linear, and it's not so difficult to see that it's also bounded. Okay, so how do we show that this is linear? So how do we show that this is linear? The point is, okay, so to check that it's linear, you check in a sum of two vectors, T of x plus y. But this guy is just, by definition, the limit when n goes to infinity of Tn of x plus y. But now we use the linearity of Tn to say that this is the same as the limit when n goes to infinity of Tn of x plus Tn of y. But now the property of the limit, and each guy of these ones has their own limit. So then this is just the limit when n goes to infinity of Tn of x plus the limit when n goes to infinity of Tn of y. But now taking this limit, you get that this is just T of x plus T of y. Okay, so this checks the linearity for T of x plus y. Similarly, T of alpha x is equal to the limit when n goes to infinity of T of Tn of alpha x, and then you do the same computations as we've done here, and we get that this is alpha T of x. Okay, so then T is linear. Okay, so one way to show that T is bounded is just by showing that Tn, now we are missing to show, we need to show that Tn converges to T in the norm of b of xy. Okay, so in particular, if you know that Tn is converging to T in the norm of b of xy, then that means that T has a bounded norm to begin with. Okay, if not, you can actually just do it by realizing that Tn has a bounded norm. So if it's a Cauchy sequence, it has a bounded norm. Then T of x. So let's try to show that it's bounded first, which is a bit easier. So T of x is equal to the limit when n goes to infinity of Tn of x. So the norm of this is, which is less or equal than the limit when n goes to infinity of the norm of Tn times x. But this guy here is less or equal than the supremum over the norms of Tn of x, and this is bounded. The supremum is finite, because Tn is a Cauchy sequence. Okay, so if you have a Cauchy sequence, you can write the norm of Tn in terms of a bunch of differences, and you can actually show that this can actually not be so big. Okay, and this is just using the Cauchy property. So now the question is, can we show that Tn converges to T in the norm of b of xy? Okay, so now what we need to compute, or we need to show, is that the norm of T, so we can look at the norm of T minus Tn. And we want to show that this goes to 0 when n goes to infinity. Okay, so we pick an x, take an x in B1. So any x, actually, doesn't matter which one it is. So we take an x in B1. And now we know that this guy is at the supremum over all the x in B1. So we take T minus Tn of x, T minus Tn applied to x. And now we realize that this guy is less or equal, and this is by the triangle inequality. By triangle inequality, this is less or equal than T minus T of x minus Tm of x plus Tn Tm of x minus Tn of x. So basically what we had done is add and subtract T of m. So in such a way to do the following thing. So one of the things is, we know that for every x, there exists an n that depend on x. For every epsilon, let's put it, for every x and for every epsilon, there exists an n that depend on x, such that the norm of t of x minus tm of x is less than epsilon over 2 for every m bigger than nx. Okay, so what I'm trying to say here is this m can be depending heavily on the point x, but I want to have an estimate which is independent of x, because now then we have to take the supremum of x in B1. So I want to have an estimate which is independent of x. So that's why I introduce summing this tm and this here, because here we'll have to take an m which is really, really large, but here we won't actually have to take an n that is arbitrarily large, because by the Cauchy property, where is the Cauchy property? So the Cauchy property says that Tn minus Tm is less than epsilon for every n and m bigger than m, a single n1. Okay, so there exists an n such that Tn minus Tn is less than epsilon over 2 for every m comma n bigger than n. Okay, so the point is that here I'm not picking an n that is depending on x for the first. It's not. I'm not picking the little n is gonna be independent of the x. So in this way, I can actually take the supremum. Okay, so this is less or equal. So then for every m, so we pick the n coming from here, and then we take the m which is larger than this n and this nx. Okay, but the estimate that I'm going to get is independent of this nx that I'm taking here. Okay, so what I'm saying is that t minus tn of x is less or equal than epsilon over 2 plus epsilon over 2 times the norm of x, which is just less or equal than epsilon. Okay, and now we can take the supremum of x in B1, and this estimate here is independent of the m that I'm taking in the middle to make this estimate. Okay, so this m is hidden. Okay, so this m is just to get this bound to be going on, but the estimate that we get is independent of the choice of this m. Okay, the only thing I have to choose is this m larger than n of x, but it's not affecting the choice of the little n. Okay, so I hope I made that clear. Okay, so that's how we finish that proof. Now, let's look at a couple of corollaries. Okay, I think this would be the most complicated thing for this whole class. Okay, so what is a corollary of this? So if we take the bounded linear function, so x is a Banach space, and b of x. So here I'm going to put R or C. So this is the field in which x is a vector space. So b of x to R or C, which are complete Banach spaces themselves, is also Banach. Okay, just by using the previous thing. So then b of x, let's say to R or C again, the linear functionals that go from x to R are usually denoted by x star, and this is called the dual space to x. Okay, so this is something I claim is quite interesting to understand. And then in particular, just to give you an idea of how the duals work, if x is equal to LP, then x star is equal to LQ, such that 1 over P plus 1 over Q is equal to 1. Okay, so if x is equal to the continuous functions in 0, 1, then x star is equal to the measures, to the Radon measures of 0, 1. If x, so here you realize that if x is equal to L2, its dual is the same, is L2 again. Okay, and this is true for Hilbert spaces in general. If you take a Hilbert space and you take its dual, the dual will be the same as the Hilbert space. But it's not true for Banach spaces. Okay, so what else do we want to do in this class? So lemma, so let's say that we have x, y, and z, which are normed linear spaces. Then let's say that we have the situation that we have x is mapped onto y by t, and s is s maps y onto z, and this guy is in B of xy, this guy is in B of yz. Then the composition SOT, which maps x to z, so this maps, so this would be SOT. This belongs to V of xz. Okay, so if you have something that is sending x to y and something that is sending y to z, then if you take the composition, this will send something from x to z. So this is also a bounded linear thing, and we have the norm that the composition S of t is less or equal than the norm of S times the norm of t. Okay, so the fact that this is linear is fairly clear. The fact that we have this norm, so let's just prove the fact that the norm satisfies this. So let's say that we take SOT of a certain x in B1. So if we take the norm of this in Z, this is less or equal than the norm of S times T of X with the norm in Y. Okay, so because S is an operator from Y to Z, so if we take the norm of Z, so we can see the composition as S applied to T of X. So then this is the definition of the norm of S. But now if we use the definition of the norm of T, this is less or equal than the norm of S times the norm of T times the norm of X. And this is in X. Okay, and this is just using that T is a bounded linear operator from X to Y. And then what we have done is that S composed with T applied to X is less or equal than the norm of S times the norm of T times the norm of X in X, which implies that the norm of the composition is less or equal than the norm of S times the norm of T. Okay, so that was just a simple proof, and then just something that people usually use in terms of notation. Notation is fairly important because if you have a good notation, it actually makes you understand what you're doing. So this is, in general, S of T is defined more like a product. So usually there is no even a dot, it's just S and T. And this is usually called a product. So you have to think in terms of linear transformations in finite dimension. If you have the composition of two linear transformations is equivalent as multiplying their matrices. Okay, so the concept of multiplication of matrices now extends to the concept of multiplications of linear operators. Okay, so the concept of multiplication of matrices extends to the concept of multiplying linear bounded operators. Okay, they don't even have to be bounded, but whatever. And so in particular, so this is one thing of notation. Another thing of notation is that if we are going to denote by b of x all the linear transformations of x onto itself. Okay, so what is the point of considering this b of x, especially with this product, is that b of x has a linear structure with a product given by the composition. Has a linear structure and has with a product given by the composition. Okay, so what is so the point is that if you look at this thing, whenever you have a linear structure with a product, then what we're going to say that b of x is a ring. Okay, so what is the lemma? Bx is a ring with identity. Okay, so the identity on b of x is just taking the linear operator that takes x onto x. Okay, so this is an identity, and whenever we take a composition with the identity, you just get your same linear operator itself. Okay, so the point is that b of x has an algebraic structure, which a lot of people use. I'm not particularly well suited to explain much about it, but this is the clear like sort of foreground into all the algebraic things that you can do. The point is that b of x is a ring, and it's not a commutative ring. Okay, so when you take products in b of x, taking s times t is different from taking t times s. Okay, so the lack of commutativity, which is true in matrices, makes these type of rings interesting to study. And what's the other thing that I wanted to say is that the product is continuous under the norm of bx. Okay, so if Tn converges to T and Sn converges to S, then Tn Sn converges to Ts. Okay, so let's look at the first part, that Bx is a ring with identity is fairly clear just by looking at these things. So the important thing is that this is continuous under the norm that we're trying to use. So what is the proof of this? So we need to show that Sn Tn converges to St. So we take the norm of Sn Tn minus St, and now we add and subtract S Tn plus Stn minus St. Okay, so then this is by the triangle inequality. By the triangle inequality for this norm is going to be less or equal than Sn minus S multiplied by Tn plus S composed with Tn minus T in norm. Okay, so now the next thing that we are going to do is going to use the lemma over here to say that the composition, the norm of the composition is less or equal than the product of the norms. So this thing here is less or equal than the norm of Sn minus S times the norm of Tn plus the norm of S times the norm of Tn minus T. Okay, and now what we can see is that if Tn converges to T, then the supremum of the norm of Tn is bounded. So let's say that this is equal to the supremum of all of this is equal to K. So then this is less or equal than K times the norm of Sn minus S plus the norm of S is just a bounded number, so we can say that the norm of S is also less or equal than K. So we can take K times Sn minus S times Tn minus T, and here we have taken K is equal to the max of the supremum of Tn, comma, the norm of S. Okay, and now if we take this guy goes to 0 when we take n to infinity, because of our assumption that Tn converges to T and Sn converges to T to S. So this guy goes to 0 when n goes to infinity, and this guy goes to 0 when n goes to infinity. Okay. What else can we do in the algebra or the ring of linear bounded functionals is that, okay, so using the products on Bx, we can define the powers of an operator. Okay, so basically we can take t squared, which is just t times t, which is t composed with t, and so t cubed is going to be t times t times t, which again is t composed with t composed with t, and so on. Okay, so in particular, if we have a polynomial for an arbitrary polynomial, so let's say p of, let's say, little t is just a0 plus a1 times t plus a2 times t squared plus a3 times t cubed plus and so on, and we can take a finite polynomial. Then if we take p of the operator t, this is just defined as a0 times the identity plus a1 times t plus a2 times t squared plus a3 times t cubed plus and so on. So the idea is, and here I'm considering p of t to be a finite polynomial, but the idea is that, so this is the definition of a polynomial function defined onto t, and we can extend this notion to any analytical function. Okay, so in particular, you might have seen this expression before. E to the t is equal to the sum from I equals to 0 up to infinity of t to the I, so t to the 0 is equal to the identity, over I factorial. Okay, and so in particular, am I missing something here? No, I don't think so. So in particular, we can take the exponential of an operator. And this guy is giving you this specific thing. So maybe sometimes people use this notation when you're trying to use the power series of something. So in particular, the heat equation is like looking like at the exponential. So if you look at ODE, dt of f is equal to Laplacian of f. This is similar to having, let's say, an ODE, which is a vector u dot is equal to a matrix. So this is a matrix times u. Okay, so then this is an ODE. And let's say we have u of 0 is equal to u naught. So, and here I was saying dt of f is equal to Laplacian of f, and f of 0 is equal to f naught. Okay? So, if you look at the solution of this ODE, what you're going to see is that u of t is, and I mean this is, one should be a little bit careful with this, but this is e to the t a, so the exponential of the matrix apply to u0. Okay, so in particular, the solution for this PDE, and so here I put the Laplacian, but here I could put any linear operator a of f. So now a would be a bounded operator from L2 to L2, and actually we don't even need bounded operator, so we just need an operator a that is go from L2 to L2, which is linear, and we have the same formulation. So the solution to the heat equation usually is written as f of t is e to the t Laplacian, where Laplacian is considered now as an operator, and this e of t Laplacian is given by this formula here, times f naught. Okay, so this is the operator e to the t Laplacian applied to f0. Okay, so sometimes having this structure sort of reduces like a lot of the, having the good notation gives you a good idea of how this is behaving. So this heat equation can be seen really similarly as what is going on with this ODE. Okay, this is linear ODEs. So a PDE, a linear PDE, can be understood in a similar way that the linear ODE is being understood. So and one of the things that with this ring structure and this algebraic structure is that you have to be careful that these guys are not commutative. So the same as matrices, A times B is not equal to B times A. Okay, so non-commutative algebra. Okay, and this is the most interesting type of algebra, but I don't do algebra, so I don't actually know much about this. Okay, so let's finish this somewhat short class with exercise of the book. So this is exercise 4.13, and here we are considering t that is going from little l2 to little l2. So I think we have seen this example before, such that t of x1, x2, x3, x4, and so on is mapped into 0, 4 of x1, x2, 4 of x3, x4, and then you follow the same pattern. Okay, so you multiply by 4 the odd numbers, and then you leave the other ones the same, and you shift everything to the right. Okay, so this is a shift operator. Okay, so the question is, what is t squared equal to? So what happens when you're doing this shift and multiplying by 4 in the same things? Okay, so how do you compute t squared? So we have to take t squared of x1, x2, x3, x4, and so on. So, but this is the same as t applied to t of x1, x2, x3, x4, and so on. Okay, but t of x1, x2, x3, x4, and so on is what I've written up there. So this is t applied to the vector 0, 4x1, x2, 4x3, x4, and so on. Okay, but now I need to consider this as my x1, this as my x2, this as my x3, this as my x4, and this as my x5. So what do I have to do? I have to shift 1 to the right, and the odd numbers, odd places, I multiply by 4, and the even ones I remain the same. Okay, so what I'm going to obtain is that this is 0, 0 times this element just the element in the second position just moves 1 to the right. So the element in the x2 position just moves 1 to the right. So this is 4 of x1. The element in the third position moves 1 to the right and is multiplied by 4. So this is 4x2. And now if I keep going with this rule, this is 4x3, 4x4, and so on. So in particular, what you get is that this is equal to 4 times 0, 0, x1, x2, x3, x4, and so on. So basically this is 4 times a shift to the right, which we have seen in a previous class that a shift to the right is actually an isometry. So one of the things that the question makes you realize is, what is the norm of t squared? So the norm of t squared, we can realize, is 4 times an isometry. So t squared is 4 times an isometry. So this is equal to 4 because t squared is equal to 4 times an isometry, which is shifting positions to the right. Okay, but this is very different from the norm of t squared. So the norm of t, as we can see before, so the norm of t is equal to 4. So then the norm of t squared is less or equal than the norm of t squared. This is the lemma we proved before. So this is the lemma of the composition of SOT is less or equal than the norm of t times t. So the norm of t squared is less than the norm of t squared. This guy is equal to 4, but this thing is equal to 16 because the norm of t is equal to 4. Okay, so this is not a sharp bound. Okay, so this is just for you to have to be careful. When we do these things might not actually be sharp bounds.